So, we looked at transmissivity in yesterday's class, and so there can be surfaces or media which are non-opaque, which will allow some radiation to pass through, and now when radiation passes through such non-opaque media, generally they are participatory in nature because there can be emission because of the temperature of the medium being greater than 0 Kelvin according to Provost's law. It can also absorb, it can also scatter. Scattering is basically reflection, but scattering is from the volume. So scattering is of two types. There is in scattering, that is reflected inside, and out scattering is that which is going out. So the net will be scattered, whatever is scattered out minus whatever is scattered in. So this scattering could be a function of wavelength. The scattering should be can be also be a function of the angle, okay, if it is not isotropic. So if you have anisotropic spectral scattering and all that, and so the what will determine the scattering? Scattering will depend on what apart from the angle and this thing. For example, surface in a volume, for example in the atmosphere, it should depend on the size of the particle, okay. So the scattering by a dust particle will be different from scattering by a water molecule, which will be different from scattering from ice, and these ice can be of different shapes. We need not always assume that it will be spherical. If it is oblate and if it is non-spherical, then the scattering theory becomes very involved. So radiation heat transfer people as well as optics people and physicists have worked out extensive theories to handle scattering. So this is called Mie scattering theory, Rayleigh scattering theory, and so on, okay. So there are algorithms which have been developed, we call the T matrix algorithm and all that, which can handle scattering. So scattering is very involved. If you are doing such kind of calculation, you are in the forefront of radiative heat transfer research. You are able to handle scattering in molecules, scattering in the atmosphere and all that, okay. Now we look at some simple problems, so that whatever concepts we have learnt in yesterday's class and whatever definitions we have learnt, essentially they are reinforced, okay. Problem number 15. Please take down this spectral distribution of alpha as well as rho, okay. So only one wavelength is given, that is 1.5 micrometer, alpha lambda and rho lambda are given, okay. Once you are through, you tell me, I will start dictating the problem. Okay. All right. Problem number 15, the spectral absorptivity alpha lambda. The spectral absorptivity alpha lambda, and the spectral reflectivity rho lambda, and the spectral reflectivity rho lambda for a diffuse surface are given in the figure. For a diffuse surface are given in the figure. Alpha lambda and rho lambda for a diffuse surface are given in the figure, full stop. A, sketch the spectral transmissivity distribution. A, sketch the spectral transmissivity distribution. A, sketch the spectral transmissivity distribution. B, if solar radiation, with capital G, okay, if solar radiation with G equal to 800 watts per meter square, 800 watts per meter square. So if solar radiation with G equal to 800 watts per meter square and spectral distribution corresponding to a black body, and spectral distribution corresponding to a black body at 6000 Kelvin. Black body at 6000 Kelvin is incident on the material. determine the fractions of the irradiation, determine the fractions of the irradiation that are absorbed, reflected and transmitted by the material, Problem clear? Okay. So, this is basically a fundamental problem where we move from one property to another property, and this is for the first time you will be calculating tau from tau lambda in this class, in this course. Okay, please start. For the benefit of people who came late, for a surface I have given alpha lambda and rho lambda. So, solar radiation is falling on it. For people who came late, alpha lambda and rho lambda are given. Incident radiation 800 watts per meter square, irradiation, sun temperature 6000 Kelvin you can take, sketch tau lambda and get alpha, tau and rho, and hence find out the fractions. No, alpha lambda plus rho.
And alpha lambda plus that also will be given.
Which one?
All only total hemispherical quantities which should be sum common or directly from this also.
Total will be also equal to 1. That can be proved from the derivation itself. Okay. So, the first part of the question is, so the first part of the question is, from these two distributions we have to get the distribution for tau lambda. So, the basic equation we use is this comes from energy balance. This is with regard to the incident radiation. Okay, do not worry about the emission, do not get confused. Emission is a separate story. Tau lambda. So, up to lambda equal to 1.5, from 0 to 1.5 what is the story? This is 0.25, this is 0.125, 0.375 will be the sum. So, 1 minus 0.375 is 0.625, okay. Where will that fellow come? Here. After that, E is already 1, this 0, therefore this got it. We do not have to determine the transmissivity, but at least two properties must be known, right? Okay. Now we go to part B. What is part B? We have to get the individual properties. So, I have to get alpha, right? I have to get at least two of the three properties. So, I just cannot get rho and say that tau equal to 0, and but I know the f function from the f function charts. If I apply it once, I can calculate two properties, correct? So, first we will write the formula for alpha. I can also write this as is it okay? Okay. Now we will keep this. I will start erasing from here. So, correct. Okay. Now to get this 0 to 1.5 divided by 0 to infinity, what do I use? I use the f charts or f function chart. So t is already given that T equal to 6000 Kelvin. What is this? 0.89. Okay. Once you have this, so alpha is it correct? 0.332. So the absorptivity of the surface is 0.332. What absorptivity is this? Solar absorptivity. Okay. If it is absorbing radiation, let G be 800 watts per meter square, but if it is coming from from a source at some other temperature, it will change because it has got a spectral characteristic. Okay. That is why we are able to employ what are called selective surfaces. What is a selective surface? A selective surface is one which will have poor emission in the infrared and high absorptivity in the solar part of the spectrum. For what application do we want a surface like that? For a flat plate collector, we want high solar absorptivity and poor emission. It is possible to have some surfaces like this. But if it is a sun control film, in this room those windows you want to put sun control film, or in your car you want to reduce the radiation and all that, then it is a transmittance or transmissivity we are talking about. By the way, we have introduced the quantities as reflectivity, absorptivity and transmissivity. Some authors, if you look at some books, they will say reflectance, transmittance and absorptance. It is essentially the same, it is basically a nomenclature, there is no difference with. Okay, so the transmissivity of this glass, what happens is the transmissivity cannot be changed. In the sun control film we will see in the next problem, but the range of the wavelength range, a band in which it will transmit is different. It will cut out certain wavelengths. Okay, it acts like a pass filter. Therefore, overall you will get of the solar radiation certain portion is cut. They claim no 40% cut, 50% cut and all that. But that you can see that actually this thing is coming down. but from inside you can see outside, from outside you cannot see inside. Okay. Now you have calculated the alpha. Similarly, rho, okay. Do not quickly declare that rho is equal to 1 minus alpha, then you are doomed. Okay. There is a transmissivity in this problem. Okay. So rho, what was rho here? Is that correct? How much was it? Okay. So can you fill up this? In fact, I called it as G. I asked you only the fraction, but it is good to put everything in terms of watts per meter square. Nothing wrong in doing that, because already by determining alpha, rho and tau we got the fractions. If you want to reword the problem. Vikram, you finished? Yeah. What is this I absorb? I reflected 88 point, I transmitted 4. Okay. So I can develop the problem further and all that, but I will leave it here. I can say part C, if the surface is at a temperature of 325 Kelvin, what is the emissivity of the surface? Part C. Part D, what is the net radiation heat transfer of the surface? Okay, we can keep on developing the problem, but now it is sufficient for us because we know how to calculate tau. Now we will solve a problem where we consider two surfaces, plain glass and tinted glass, so that you are able to appreciate, you are able to evaluate whether there is any benefit of using tinted glass. They are also claiming, no, in your glasses also you have tinted glass, photochromatic and all that, right. Let us see whether there is any benefit in doing that. Is this problem, is this clear? Okay.
Question is given that radiation corresponding to black body at 6000 Kelvin is also incident on the surface.
G800 and which is equivalent to this thing. Okay, how else you want to do? You are thinking that apart from this something is there. No, even if I tell black body at 6000 Kelvin, how will you actually calculate? How will you actually calculate? You want to integrate from 0 to infinity. That is 1353 watts per meter square, man, that is coming from this thing, and then it falls into the atmosphere and this thing, so many stories are there for that. That does not exactly reach. Okay, black body for 6000 Kelvin, then from there, so you can calculate the solar constant, from there atmosphere, so many things are there. he is having a very important doubt. Many of you should have got this doubt and it must have made you uneasy and all that, but luckily somebody has opened it up. Basically there is nothing wrong in our first of all there is nothing wrong in that question, but so it is my responsibility to clarify. We are not saying that it is actually the radiation is actually from a black body at 6000 Kelvin. The nature is corresponding to the black body at 6000 Kelvin. If I know 800 watts per meter square, that the variation is like that. Since I am using only the F function chart, I am using it in the numerator and denominator to find out what is the band between lambda 1 to lambda 2, what is the fraction. So to the limited extent that using this information I will be using the F function chart, this it is okay for me to consider this source to be a black body at 5800 Kelvin, but it is quite different from actually the irradiation coming from a black body at the nature of the distribution is like that. Qualitatively with lambda the irradiation varies like this. So it helps me only to calculate alpha, rho and all that, but if you want to know how much is reflected, how much is transmitted and so on, I need to know how many watts per meter square is incident. Are you getting the point? With just the information that it is a black body at 6000 Kelvin, it will lead to erroneous answers. I may get 1353 or something. For that I require other information. What else do I require? The diameter of the sun, diameter of the earth, the distance between, so many things I require. Why do you want to get into all this? If I do all this, you will get that 1353. That is a solar constant, but that 1353 is just which is entering outside the earth's atmosphere. Then so many things are happening because of carbon dioxide, water vapor, so many things, and it is okay, fine. Same thing with the transmissivity also. This black body story helps us to use the F function chart and get the properties. Okay, fine. Now we will solve another interesting problem. Problem number 16. The spectral transmissivity of plain and tinted glass, the spectral transmissivity of plain and tinted glass can be approximated as follows. Okay, plain glass. Okay, it was a transmissivity of 0.9 in the band 0.3 to 2.5 micrometer. Okay, what about this tinted glass? Same thing. So tinted glass is also 0.9. What's the big deal? Why everybody is trying to sell the tinted glass? Why is the tinted glass more expensive? The range must be more or less transmittance. It should have a same transmissivity over a narrow spectrum, narrow band. In fact, it has only between 0.5 to okay. So the spectral transmissivity of plain and tinted glass can be approximated as given on the blackboard. Outside the specified wavelength ranges, the spectral transmissivity is 0 for both the glasses. Outside the specified wavelength ranges, the spectral transmissivity is 0 for both the glasses. compare the solar energy that could be transmitted. A, compare the solar energy that could be transmitted through the two glasses. Do not get confused though, it is not one after the other, okay. Compare the solar energy that could be transmitted through the glasses. Hang on. B, with solar radiation incident on the glasses, with solar radiation incident on the glasses, compare the visible radiant energy, compare the visible radiant energy that could be transmitted, compare the visible radiant energy that could be transmitted by the two glasses, okay. There are 4 parts to this problem, because part A 2 calculations, one for plain and tinted, part B 2 calculations for plain and tinted. So, please start solving, I will take attendance and we will complete this problem, and with that the story of the properties is over. Shall we start solving? So, first A, plain glass. So, tau correct, but I do not know how I lambda I varies with lambda, but I have equivalent information. What is it information? I lambda is qualitative equal to that irradiation from a black body at 5800 Kelvin, that is the sun's temperature. Therefore, now I can get rid of this. Okay. So, 0 to 0.3 I do not have to worry about that integral and all that, right. Okay. Now, to do this, so what did you take T as? I have taken 5800, okay. We will take everybody is, how many of you have taken 6000? Okay. So, 6000 is easy, no? But the correct temperature is only 5800, okay. Let Ts be, we have to get 0.3 lambda 1, right. f of 0 to lambda 1, Sampath, how much is it? 0.03. F of 0 to lambda 2, 929, 92, lambda 1 to lambda 2, 929. So what is tau? 0.84 or 86? 84, huh? Okay. I wrote it with the purpose so that you do not get confused, 1 minus into 0 and all that, I made it complete. Second term alone is important, fine, okay. Now tau equal to 0.86, huh?
0.56.
This one 0.8.
0.84.
0.84. So plain glass, how much of the incident energy is transmitted? 84% is a lot, no? Too much. Okay, that's why inside the glass surface you feel, they say glass house and all that, no? You put a glass and they can grow plants even in cold places. Okay, glass has a terrific transmittance, that you can see, right, because you can feel it, right. Now what is the story? The tinted glass, I know that because that the wavelength range in which it permits radiation to be transmitted is smaller, narrower compared to this, I expect it to behave better. Okay. So let us say tinted glass. Now lambda 1 is what for tinted glass? No, lambda 1, lambda 2 1.5. How much is it? 0.273. Correct. I am writing out the formula in full so that we do not so that we know that we are not making any mistake. Now tau is 5 huh? So the incident radiation is 800 watts per meter square. For example, if incident radiation, okay, let us say incident radiation is 1000 watts per meter square, the plain glass will allow 840 watts per meter square to pass through. This fellow will allow only 550 watts per meter square pass through. Out of every 1000, 290 watts per meter square are stopped. So there is a advantage of 30%, that is clear, 85, 55. So it cuts out the radiation by 30%. It depends on which way you look at it, but rough calculation is for out of the incidence 30%, 30% it will cut. That is why your 3M sun control film, Garvare sun control film and all that, they will say 30%, 40% and all that. If you paste it, some 30% you will get some benefit, right. This is increasingly relevant because now the current trend is to have glass and steel structure everywhere. We are copying the West, we are aping the West, okay. That concrete and this thing, wood anyway is out, wood, aluminium, this thing, slowly it is only glass and steel, everything is okay. So it is very easy to stone all these buildings now. So because of this, no, it happens, no. So all these Bangalore people are always worried whenever there is something happening in Bangalore, because all these software companies are all having glass and steel structures, okay. They are not very secure, very easy, only few stones are required. So therefore if you want to reduce the air conditioning load, you have to look at some energy solutions like this, okay. This is only the first part of the story. Let us do the second part. Out of the solar, what about the visible part of the spectrum? Even the city buses now, all these Volvo buses, there is so much of glass, there is so much of glass in the bus, right. Nowadays if you see the front fully, so side everywhere it is glass, okay. So if the air conditioning load and all that, you have to work all these out. Now part B, so performance in the visible part of the spectrum. So that is something we have to see. So the visible part of the spectrum is 0.4 to 0.7, okay. So for part A it is very easy, part A is very easy. How much is transmitted? No, for the tinted glass, I am sorry, for the no, for the plain glass. What 0.84? 90% of the visible radiation is transmitted, because within the visible band its tau is 0.9. 0.84 is the total part of the spectrum. Are you getting the point? No. Okay, when I write it out it will become clear, okay. 1 plain glass, what is the ratio we are looking at? What is the total radiation corresponding to 0.4 to 0.7, that is the denominator. Denominator is all not 0 to infinity. If it is 0 to infinity, you already solved, man, first part. If you consider only the visible part of the spectrum, denominator is also 0.4 to 0.7, numerator is 0.4 to 0.7, but fortunately for us there is only one value 0.9, therefore 90%. So the visible part, so it does not cut out any this thing. If there is lot of daylight outside, there is daylight inside also. 90% of the lighting available outside is there inside, but the second fellow does a lot better. Can you work out the value for the second one? So Samarjit, thinking hard, is it okay? But the beauty is the numerator from 0.4 to 0.5 tau lambda equal to 0, okay. So some blue light it is cutting out, what is the 0.4 to 0.5? Blue, right, violet, blue and all that. So that violet, blue, those colors, that part of the radiation this fellow is cutting out. Therefore that is why they will look different. Your dress will look different in a tinted glass, it won't be, it will be surreal colors, it won't be the real color, it will be something different, okay. Now that is why sometimes it is you can have better surfaces which will cut out lot of radiation such that visible part of the spectrum, so that we cannot from outside we cannot see inside. That is why in many cities the police is now prohibiting people from using dark sun control films in the cars. It is not allowed, you know. Anyway, in the front portion, in the windscreen you will not use because you want to drive, you do not want to get killed, right. So that nobody uses, only the first, if you people who are having cars will know, the first 4 inches alone will close, after that it is open, but the side and back we will use. But now there are certain sun control films which are banned by the police, because that you can see, instead of 50% if it become 30 or 40% it will be very dark inside, you will not see, even somebody is going strutting around with some arms and this thing is having a assault rifle and all that, we do not know. Lot of such things happen in Delhi and all that, isn't it? Every day you are hearing stories, somebody they take a gun and shoot. It's not only in the US, it is happening in our NCR, National Capital Region, okay. So the police people have said remove all this, only certain types of sun control film are permitted. Now if you do this, then what was this? Is that correct? 0.9 into divided by okay. So what is that ratio? How much? 0.9 into .49 minus 0.25, is it? How did you do that? 0.516 my 0.2 divided by, is it 0.51? 516 minus so from 90% we brought it down to 60%, okay. So it cuts out the visible part by 40%, you get an advantage of 40%, okay. So this then you can extend this concept and all this, then for example based on the emission, Based on the emission, you can also devise instruments to measure the temperature, for example, so the temperature of a surface. Okay. So if you that is the basis of an optical pyrometer. Okay. So you can suppose the surface is in the background. The surface is in the background. What happens is you can devise a system of lenses. You can focus on that and focus on the radiation coming from the background. Then you have a filament. Okay. This background is at a particular temperature. This filament's temperature can be controlled because the filament is connected to some, okay. You keep on increasing the voltage such that its temperature increases, then depending on the Planck's distribution this thing will also characteristics also change, right. You can change the setting such that at a particular point this filament has the same temperature as the background, then what will happen is since this merges with this, then this filament will disappear from your field of view. So at that point in time, the temperature of the filament is the same as the temperature of the background. Therefore this is a way of inferring the background temperature remotely. This is pyrometry. Okay. Optical pyrometer, like that basically. So based on Planck's law, based on radiation also you can devise some equipment to sense temperature remotely. Based on infrared radiation emitted from the objects, we can calculate we can infer the temperature. That is what they do in airports and all that. No, swine flu, you pass through that, suddenly if all these portions the color is different, then they will say they will quarantine you, then go to that hospital and get yourself checked. So that means there is a calibration. So what they will do is for a known temperature you will first calibrate, and you will calibrate that color, that hue. There are suppose there are 256 colors, each color corresponds to what temperature you will calibrate, then accordingly you will say blue color is this 40 degrees, red color is this and all that, and that is basically from the color you infer the temperature. So if you look at all the equipment which you are coming across in heat transfer, their design, if you want to measure something, it is based on some particular law in the subject. Okay. After that you will have to validate it with some reference. The reference with which you validate must be more accurate than this so that it can be trusted. This is how science and technology has improved in all the disciplines, right. So this is one example where you use basic radiation laws to measure temperatures remotely. Okay. So we will stop here, and the next class onwards we will look at the geometric orientation between surfaces. So very critical in the study of radiation and heat transfer. So this is known as shape factor or view factor. So we will look at view factors, lot of solid geometry, we will work out lots of problems, lots of algebra will be involved and so on. Okay.